In this part of lecture, I'm going to cover flexibility method for pin-jointed statically indeterminate structures. And this is mainly applicable to trusses, which are indeterminate trusses. And the key thing here is to determine the member forces. Ordinarily, when we have statically determinate trusses, then we use method of sections or method of joints to work out member forces. But if the number of members is more, if SI is more than 0, then method of sections and method of joints does not apply. Then you have to use either force method or flexibility method to work out member forces. And today we are using flexibility method to work out member forces in pin jointed structures. And a typical example of pin jointed structures is a truss.
Hey friends, if you're new here, I am Dr. Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life.
How to determine static indeterminacy in pin jointed structures? We use these formula. So M is number of members. When we have a lot of members, then we do not use this simple formula. And J is number of joints, including supports. R is total number of reactions. SI is degree of indeterminacy. Now this is for two-dimensional planar structures. Number of equilibrium equations are 2 times J. And there are 2 equilibrium equations in trusses. So we do not have summation of moment because moments are not there in trusses. So that's why at each joint we will have force in X direction and force in Y direction. Total number of unknowns are sum of axial forces in member, i.e. M forces, plus reactions. These will be your U. So U is equal to M plus R, means member forces plus reactions. And in trusses or in pin jointed structures, you can only have tension or compression. That is one axial force. So that's why it's 1 times M. If it was a beam or a frame member, in beam or a frame member, you will have 3 forces. You will have moment and you will have axial force and you will have shear force. In a beam element, you will have, or a frame element, you will have 3M. R will be revised as well. But this is for pin jointed structures. The total number of unknowns are M plus R. Again, this is telling you if U is equal to the equilibrium equations 2J, then it's determinate. If it is less than equilibrium equations, then it is collapse. And if it is greater, then it is indeterminate. The formula for finding out static indeterminacy is U minus E. Now here U is M plus R for 2D pin jointed structures minus 2J. 2J is number of equilibrium equations at each joint. At each joint, certainly you will have only 2 forces, Fx and Fy. That's why it is 2J. Now, how about 3D pin jointed structures? In 3D pin jointed structures, you will still have only axial forces. So this will not change. So M plus R will not change because in trusses, you will have only axial force. But number of equilibrium equations will change because in truss, a joint can move in X direction, in Y direction, and in Z direction. So that's why it is 3J over here. Now, how about 2D rigidly jointed structures, fixed structures? In each member, you will have 3 forces, which will be axial force, tension or compression, and shear force, vertical load, and moment. So that's why we have this 3M here plus R, because it's a frame element. It is rigidly jointed structure. Minus 3J. Each joint can move in horizontal direction, can move in vertical direction, and each joint can develop a moment as well. So that's why it is 3J. For 3D rigidly jointed structures, you will have 6 forces in a member. So a member can have axial force, it can have bending moment, and it can have, so it can have forces in 3 directions, it can have moments in 3 directions. So that's why it's going to be 6M plus R. Equally, you will have 6 joint forces as well. So these are different formula for different types of structures.
Let us start with theoretical background.
And then I'm not going into too much details of the theory when it was developed, so you can read these things yourself. But the key thing here is principle of virtual work. How do we apply this method? The way we apply it is that first of all, we need to work out SI. If SI is, for example, 3, then we will remove 3 members and then we will have a real system and we will have 3 virtual systems, and with the help of those we will work out the deflections, and as a result we will work out the forces. If I apply, it is called unit load as well. So if I apply unit load and deflection, it can be written as summation of all forces into E. My total deflection is going to be summation of forces. P prime is the virtual system. So total forces in the virtual system times the E, which is the total deflection in the real system. E is equal to P ln over an, where P is the force in real system, L is the length, A is area, E is modulus of elasticity, and again L alpha and Tn, this is related with the temperature, and lambda is related with the manufacturing imperfections. The key point here is that when we apply a unit load to the real system, it can be equated to summation of forces in virtual system times E. E is the elongation in real system. I can write this entire equation is I can replace this En with the entire bracket. Then you will have P dash force in the virtual system and then all this which is coming from E. So this is the main building block which we will be working on. So if I ignore manufacturing imperfections and temperature changes for a minute, it will be P dash P L over An and summation of that. So that will be the key to working out the deflection in a real system. So once we have this deflection in the real system, then we can work out the member forces from that. Then it comes to principle of superposition. So what do we do? Firstly, we determine SI, static indeterminacy, and then we specify which forces or redundant need to be removed so that the structure is statically determinate and stable. If SI is equal to 4, then you have to remove 4 members, but the structure has to be stable and determinate. It can't be unstable. And then you work out displacements at those positions. Then you have to work out compatibility equations for displacement or rotation at each point. The equations can be obviously expressed in terms of unknown redundants and determine all the deflections. And then equilibrium equations to determine unknown reactions.
Let us solve one example on indeterminate trusses.
What do we do in this case? In this case, we have SI is equal to M plus R minus 2J. We can see that static indeterminacy is 2, which means that 2 members have to be removed. So now we have removed 1 member and the second member. Then we have to make cut at these points and we have to remove 1 member at a time. Then it will have these redundants when we remove these members. System 0, which is statically determinate, and P naught can be estimated. System 0 is the one which we obtain after removing the redundants and replacing it with the kind of displacements that will happen at those positions. So for the first one, we will say D10, and for the second one, we will say D20. This is termed as initial solution. And then we will have the compatibility equations. For compatibility equations, we will have system 1 and system 2. We will have 2 virtual systems. In the first one, we will replace the first member with a unit load. And then we will work out these flexibility coefficients. In the second system, we will apply unit load at 2 locations. Then we will work out those flexibility coefficients. Flexibility coefficient F11 means that load at 1 due to applied unit load at point 1, node 1. Flexibility coefficient at 2 due to applied load at 1. And again here you can say that if this is F12, it means that the load is applied at node 2. And then how do we assemble them? So for compatibility of equations, we will have D10 plus F11 R1. R1 is the redundant force that we removed from here, plus F12 into R2, and D20 will be equal to F21 into R1. This is in case of if we need to make 2 cuts. If we need to make only 1 cut, in that case we will just have D10 plus F11 R1, and from there we will work out the member forces. And then finally the total solution will be initial plus complementary. The initial one was P naught plus P1 into R1 plus P2 into R2. and from there you will work out the total load in the member. This system is for when we have SI is equal to 2. Imagine if SI was equal to 5 or 6, then how many equations would you have? If I wanted to solve the same question with the help of some software, it will take me probably less than 2 minutes to solve it and see the results. The main aim of learning these problems is that we understand how much work is involved, what happens in the background, and how do we implement different procedures so that we can work out the member forces. Okay, then we have these compatibility equations. Then D20 is going to be with this equation that we covered a bit earlier. Now I will quickly go to example. These are different compatibility equations if we had to make two cuts. I will quickly go to example. Now calculate the member forces. The area of members is as follows. The area of ABC is 10 and BD and CD, these are members, it's 20 centimeters square. The modulus of elasticity is constant for all members. Assume tension is positive. So we always assume tension is positive. So first thing first, we have to apply principle of superposition, which means that we have to determine SI and decide what degree of freedom needs to be removed. So SI for this structure is M plus R minus 2J. And if I apply this is not a member, it is a kind of support. It is giving me SI is equal to 1. Which means that I need to remove one force. It could be a member force, it could be a support as well. But the easiest thing for me is to remove this member BC to make the structure statically determinate and stable. I have decided here to cut this member, and when I cut this member, then I will generate system 0 and then I will generate system 1 or virtual method. System 0 means that imagine if this member was not there and then work out the member forces, because that's going to be a determinate structure and I can easily use method of joints to work out member forces. And system 1 or virtual method would be the one when I will apply a unit load at the point where I have removed the member. And then I will combine these two. Now the first thing first, I have to determine the member forces for system 0. This is our actual structure, and system 0 means that I have removed this member BC. So when I remove this member BC, it means that this member is not there. And then I will use these signs. Arrow pointing inwards indicates that these are tension members. If my value is coming out to be negative, it means that it is a compression member. So first I will start with a joint which has got some kind of unknowns for applying this method of joints. So now I have this joint C. At joint C, 60 kilonewton is applied. Slope is given. This dimension is 600 over here and the vertical dimension is 450. And then I can work out the hypotenuse. Now, how many forces are there? I have one vertical force, I have one horizontal force FCD, and I have one inclined force FAC. Now, I have to resolve first of all this FAC into horizontal and vertical component. The vertical component is going to be upwards FAC sine theta, and sine theta is equal to vertical dimension divided by hypotenuse. And horizontal component will be equal to FAC cos theta, and cos theta will be equal to horizontal dimension divided by hypotenuse. Now I will use summation of vertical and horizontal forces equal to 0. So first of all, summation of vertical forces equal to 0. Now you can see that these forces are acting in opposition to each other. I have FAC if I think that axis is positive like this, X and Y. When these are acting in opposite direction, they will have opposing signs. Then if I sum them up, I will say 60 minus FAC, this value is equal to 0. But I can directly say that these are equal to each other. So which means that FAC into these values is equal to 60. From here, I can work out FAC as positive. And then I can simply write FAC over here. The next thing for me would be to use summation of horizontal forces equal to 0. I have FCD. I have this another force in red, which is the component of the inclined force. Both are in the same direction. So then if I add it up and equate it to 0, one is going to be in negative, because if I bring it to the other sign of the equation, it's going to be negative. That is the reason FCD is equal to minus FAC into 6 over 7.5. Now this will give me FCD as minus 80. So then I will write FCD or FDC is one and the same thing. The next thing is I will move to joint B. At joint B, I have FAB and then I have FBD. Again, dividing it into components, it will give me this value. First of all, tell me what would be vertical component here.
450.
0.
What will be vertical force? There's no other vertical force, so that's why the vertical force is going to be 0. And if BD is equal to 0, it means that its horizontal component is going to be 0 as well. And if this is 0, if there is no other force, then FAB is going to be 0 as well. So both of these forces are 0.
So when choosing to remove one of the members, could you choose to remove a zero force member?
No, you don't have to. You can remove any member as long as your structure remains stable. Now we have, I think, pretty much all the member forces. Now we have determined all the member forces for this system 0. The next thing is we will apply a unit load at a point where we remove the force. We will apply a unit load at a point where we remove the load, and we will call this factor as F11. This is flexibility factor. Now in this case we will not start from joint C. We will start from joint B, because always start where at least you have one known force. Now here at joint B I have one force, vertical force, which is 1, and I have this inclined force FBD, for which horizontal and vertical dimensions are given. I can work out the hypotenuse, and then I have to take horizontal and vertical component of FBD, which are here, and then now I will sum up these forces. Now remember, the direction of forces is in the same direction. So if I sum up 1 plus FBD, 450 over 750 is equal to 0, then if I bring it on the other side of the 0, it's going to be negative. So this is the reason it is negative. Negative means that my initial assumption was wrong. This is going to be in compression rather than tension, because tension is positive. Then again I will sum in the horizontal forces. Again I will sum these forces. So when I sum these forces and put the value for FBD, I will get value of FAB as 4 over 3. And then I will move to joint C. Because I moved the member, it means that I have one applied at this joint and one applied at joint C as well. So it's a force in the member. I will make horizontal and vertical components of these red things, red forces. Again, from here I can work out the member force, FAC. So FAC is going to be 5 over 3. FCD is going to be 4 over 3. Because this is symmetric, it makes sense that the forces in AB and AC are going to be same as in BD and DC. Now I have this information for virtual system and for real system, and then I will write this equation. Now previously I had two unknowns. In that case, D10 plus F11 R1 plus F12 R2 is equal to 0. But because I don't have any other force, I just have one redundant remove, so that's why I will use this equation, the compatibility equation. And now, as you know, that D10 is equal to P1 into E0. P1 is the virtual system, and E0 is the 0, means it's a real system. And that real system, discarding the manufacturing imperfections and other temperature changes, is equal to P0 L over AE. And F11 will be equal to P1 E1, which means that E1 is going to be like this. Now I have this two formula. With the help of these two formula, I will generate a table for all members. A is given, E is constant, and P0 in AB and BC, AB and BC is 0. Then P1 has got some value. So I have taken all the forces from this system 0 and system 1. And then you multiply it with LP0 P1 over AE and LP P1 P1 over AE. Now this is, when you sum it up, this is actually D10. If you go back and come from the previous slide, what we have done is that we have worked out these values and we have worked out these values in the table format. Now once you have these values, simply you put this into this equation D10 F11R, and from here you can work out value of redundant. So value of the redundant force, that will remain 30.3 kilonewton. The final member force is equal to P naught, the initial force in that member, plus redundant that we found out from here, and into P1. The way it works here is that we will take out P naught for this member, which is 0, plus R, which is 30.3, times 4 over 3, and then we get this value. In the same way for the second one, P naught is 0, plus R is 30.3, times 1, it results in 30.3. And in the same case, P naught is minus 80, plus 4 over 3, into 30.3. This is giving me minus 39.3. Again, repeat the same process for all the loads. This is coming from this formula. And in the same way, you simply bring these values on the diagram itself. Now, this is telling you that, okay, tension is happening here. Our sign was fine. Now, compression is happening in member DC. Tension is happening in this member AC. And then we get the member forces. Now, the purpose of these member forces is that we want to design it. If you wanted to design these members, probably take the maximum compressive force, BD, and DC. The maximum force is minus 50.5 kilonewton. So design them as compression members or columns. AB, AC, and BC. The maximum force is 49.5 kilonewton, and design this as tension member.
Dr. Qureshi,
Yes.
can we go back to the problem, the solution, please?
Yes.
I just wanted to understand what you did. So you didn't eliminate any members physically.
Yes.
You determined the force.
Yes. I did not eliminate any forces. For analyzing the structure, I removed this member and then I applied a unit load to this member. So just to sum up, what we did is that first of all, we found out the SI. So which gave us indication that how many members are to be removed. If it was 3, then I will remove 3 members or 3 supports. To make the structure stable and determinate, the structure has to be determinate. I removed this member because this was convenient for me, and then I found out the system 0. It means that there is 0 force here. And then I used method of joints to work out member forces. Once I had all the forces, these were my P naughts, okay, P naught forces. And then I moved to virtual method where I applied a unit load at a point where I removed the load. So this in this entire member I have load of 1. And then I applied the method of joints, which gave me again forces in the real system and in the virtual system. And then I applied these equations, D10 plus F11R. This is the equation that I used, P1 P naught L over AE, P1 P1 L over AE. This is equal to F1. And this is the summation. So that's why P1 P naught L over AE will contribute to D10, and P1 P1 L over AE, that will contribute to F11. And for each individual member, I worked that out. And then I summed them up, and then I put them back into this equation, D10 plus F11 into R, where I have these values of F11 and D1. From there, I worked out value of redundant, which is 30.3 kilonewton. I found the actual member force, which is equal to P naught plus R P1. And I have these P naughts and P1s, I have value of R. So for each member, I was able to work out the actual force that it will develop. And from there, I had these couple of members, some were in compression, some were in tension. The negative sign indicates compression. So if I had to design this truss, then I will pick up the maximum force and I will design the compression members for compression, and I will design the tension members for tension. Does it make sense?
Thank you, Professor Qureshi. This brief summary explained.
Thanks for watching this lecture today. Click on left side of the screen to watch another video relevant to this lecture. Click on right screen to watch full playlist on structural mechanics.